Hello, it's Keith here, and this is lesson 37 of the simple series of my Z80 assembly programming tutorials. Today we're going to extend the previous bitmap example where we were drawing our Chibiko character, the mascot you can see here, and we were cropping it. Now before we were using the tilemap to draw the graphic, which meant we were limited in movement by 8x8 pixel chunks. This time we're using a set of hardware sprites, and so we can have our Chibiko character, and our Chibiko character can enter and leave the screen as you can see here, and so that's what we're doing. Now the example today, as I say, is using hardware sprites, and this poses a bit of a challenge for us. Now when we use hardware sprites, you see, we actually have to allocate each of the hardware sprites to build up the image. Our Chibiko bitmap is 48 by 48 pixels, and you can see the colours are a little bit wrong here because I haven't set them up right, I don't think, but it's running on the Game Boy Color here. It works on the Classic as well. But when we allocate these sprites, we need to allocate them according to the number the image needs. The image is 48 by 48 pixels, that's 6 by 6 tiles or 8 pixel hardware sprites, and that's 36 in total. But as the image leaves the screen, you can see it will get smaller, and this means we need fewer hardware sprites. And what I've done here is I've turned off the code that actually removes the unneeded hardware sprites, and so we're only using the number of hardware sprites that we need to draw the amount of the image that is visible on the screen. But we do need to cope with that. We need to track and keep the number updated as we build the image, and also we need to remove them when we don't need as many as we do in some cases. Now there you can see it running on the Game Boy Color, but this does work on the Game Boy Classic as well, as you can see here. So this example will work fine on both. Now what we're not going to do today is we're not going to cover the code that hasn't changed much since last time. I'm not going to discuss the example of how I'm actually cropping the sprite. Please see the previous lesson 36 to see that, because I covered it all there. Today we're just going to focus on the extensions that have been made for the hardware sprites to allow the smooth movement and that kind of thing. So let's go over to our code and let's take a look. Well, the first thing I think we'll do is we'll re-enable this code here, which was, as I say, this was me temporarily disabling the clearing of the unneeded hardware sprites. Now at the start of our code here, we have a new variable called hardware sprite num here. Now this has been given a memory address to use for its storage, and this is the current hardware sprite number because we're going to go from hardware sprite 0 to draw the first part of the Chibiko graphic, and then assuming the entire sprite is entirely on the screen, then it will be made up of 36 hardware sprites in total, and we'll track that with hsprite number. We're also going to need to cache them those because we can only transfer hardware sprites to the video hardware during a VBlank, and so we're going to need to create a VBlank interrupt handler. And I believe on the Game Boy, to use hardware sprites, it needs to be at the memory address FF80 onwards. It needs to be at a special address to do this. So we're going to transfer our VBlank interrupt handler to this memory address here. Now the data for the sprites we're going to write into memory, and then the VBlank interrupt handler is going to transfer those to the hardware sprite RAM. So we're going to have a cache for the memory, and that's 256 bytes in total. So the top byte is D0 here, and the bottom byte will go from 00 to FF for our cache there. Now our interrupt handler actually needs to appear at memory address 40 in the cartridge here. So we've got to jump to that here. That will be executed when the VBlank occurs. Well, now what we need to do though is we need to transfer our copying routine into the correct memory address, as I say, at that FF80 memory address. So we've got this DMA copy function that I've written here, and we're just transferring this to the VBlank destination here. This DMA copy is the actual commands that will transfer the cache into the sprite memory in the video memory. So this is the routine, and it's very straightforward. All we're doing is we're using memory map function ff46. We write the top byte of the cache address to that, and that will start the DMA, and this is a direct memory transfer, so the hardware will actually do everything for us from that stage, and all we need to do is we need to just wait a little while for it to complete before we return. So that's just a simple crude delay loop to wait while the DMA transfers the data to the hardware sprite RAM. And so that's basically it. We just need to basically, it's a bit of a pain, but this routine here will do everything via function ff46, the DMA function, and that will actually transfer the sprites. So once we've got that in place in the correct memory address, and as I say, I believe it does need to be at this FF80 range sort of onwards for it to work correctly, so it needs to be pretty small, but that, if you use this one, this does seem to work just fine, and of course you're welcome to do so. Okay, so that's how we're actually getting our data to the hardware sprite memory, what actual data do we need to send? Well, it's pretty straightforward. Basically, each hardware sprite has 4 bytes, and they're in a consecutive order. So if we've got a hardware sprite number and we multiply it by 4, we will use that as an offset within our cache. Now, the Game Boy has a total of 40 sprites, and these will start, in literal sense, I believe they start from FE00 onwards. But as I say, we're actually writing to them via the cache. So all we need to do is take our hardware sprite number and multiply it by 4. And there are 4 consecutive bytes for each hardware sprite. The first one is the Y position in pixels, then the X position in pixels, then the tile number, the pattern number, and then a set of attributes. And you can see the attributes here. They vary depending on the Game Boy Color or the Game Boy Classic, but basically we don't really need any of these for today's example. We can just set all of these to 0. So that's what we're going to need to do. Now in the code, the draw player routine hasn't really changed, and that's kind of the point of these tutorials. It's pretty constant. So we've got the same settings here, but the fill area with tiles routine has been replaced with a fill area with sprites routine. This fill area with sprites works in a very similar way to the previous fill area with tiles. However, it now works with a hardware sprite number and an entry in the GB sprite cache. Now HL is being loaded with the base of the GB sprite cache in our memory, but then we're replacing the L byte with the H sprite number, which is the offset within that for the next hardware sprite. So effectively it's the hardware sprite number multiplied by 4, I guess. So that's what we're loading in there. And then what we're going to do is we're going to transfer the 4 bytes for the hardware sprite definition into that entry within the cache there. So first of all, we're going to transfer the Y position. Now we're adding 8 to the Y position because Y position 0 is actually off the screen, and so we're shifting down 8 so that we've got the correct position for the first actual sprite number that we would need, the sprite position that we would need to show for this function. So we're adding 8 there to that, and we're loading the Y position in. Then we're loading in the X position. Then we're loading in the tile number here. And we're then increasing the tile number. IY contains the tile number, remember, the pattern number that we need to show. So we're increasing that for next time. And then we're writing a 0 to the top byte, which, as I say, is the attribute. And so we're setting all of these to 0, which is just fine for this example. You might need to set a tile sprite priority if you had tiles on the screen, but for this we don't need to worry about that. But as I say, that's what we're doing there. And then we are moving across as before. This is all exactly the same as before. When we get to the end of a line, we're working in a zigzag format across and then down here, setting the hardware sprites. So after each horizontal line, we're adding any sprites that we need to skip. So if our Chibiko character is partially off the screen, we might need to skip some of the sprites. So for example, in this position here, the Chibiko is half off the left side, so we need to skip some of the patterns before we start drawing the next line, and that's what this does say. This is the same as before. And then we move down 8 pixels and we repeat again. So we're working in pixels in this case. Now, as I said though, once we've finished drawing our Chibiko bitmap, now before we draw our Chibiko bitmap, we need to set the hardware sprite number to 0, resetting it so that we'll start filling the first entry in that cache. But then once we complete, we're running clear unused sprites. Now this is just zeroing the remaining data here. So we have got this, where is it? Down here, here it is. So all this is basically doing is it is repeatedly zeroing the cache until we've cleared all 256 bytes within the cache. So that's effectively clearing all the unused sprites. So that's how we're making sure that the Chibiko bitmap doesn't trail. Now, with regards to the do crop routine, it's mostly the same as before. The only thing is now we're working in, as I say, the logical units I'm using for these tutorials work in pairs of pixels, so 2 pixels per logical unit. So we can't move with pure pixel per pixel precision, but we're close enough that I don't think it really matters. But basically, we're still having to work with a number of tiles, so because we're building our Chibiko out of 8x8 pixel sprites, so that's tiles. But we are now having to work out the offsets. So basically, as we remove a tile, as our Chibiko goes over to the left-hand side, we need to smooth out the movement so that the Chibiko continues to move smoothly. And so to do this, we're taking the bottom 2 bits when we remove a tile, and we are XORing that and calculating that as a shift. So basically, as a tile disappears from the top, we're shifting down a few pixels to compensate for that and keep the smooth movement. Now, if I remove these 2 lines and I replace this with an XOR A, effectively loading 0 into the accumulator here, Well, you see we move nice and smoothly up and down here, but then as I start disappearing, we've gone all jerky. And that's because we don't have those corrections anymore. And so that's what these two lines are doing here. They're calculating for smooth moves. So we've got that there. We've got this all is the same. We've got it here as well for the X position. And then basically finally, rather than converting to tile numbers now, we're now working in pixels now. The routine that draws the sprites to the screen also works in pixels actually. It uses a pixel width and a height, but the width and the height need to be a multiple of tiles in this case. So we're converting from logical units to pixels in these cases by doubling them all, effectively going from a logical unit base, which is pairs of pixels, to individual pixels. So that's how we're doing things here, and that's what I'm using for today's example. So it's not too bad. It's a bit of a pain working with the cache, but you know, it works pretty well. And if this code does seem to be fairly reliable. So as I always say, you can go to my website and download the source code and the build scripts, and you're welcome to use them in anything you want of your own. So if you're writing your own games and you somehow find that my example code for working with sprites is useful to you, go ahead and use it in any way you want. You don't need to give me credit or anything. I always need to say that because maybe some people want to do that. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.